For today's notes, you'll need in-class 78. This is the second part of Standard 18, and we're going to learn about chords today and all of the things that are true when they are in circles. As a refresher, chord is a segment that has both endpoints on the circle. And these chord theorems are actually what we call biconditional statements. So a quick introduction to what a biconditional statement is. It's a statement where there are two true statements that are combined using the phrase if and only if. Sometimes that's actually abbreviated as IFF. So the word if with two F's attached. So an example of a biconditional that we've learned earlier in the school year, a point would be considered a midpoint if and only if it divides a segment into two congruent segments. So what that means is that we can read the sentence forwards and we can read it backwards. So we would call something a midpoint if we could see a segment that was divided into two congruent segments is happening, or if we see a segment is divided into two congruent segments, then we can call that point a midpoint. So it's true in both directions. So we have three biconditionals today that are true for chords. The first one is that arcs are going to be congruent if and only if the chords they intersect are congruent. So in this picture, we see the chords that are congruent, which leads us to the conclusion that the arcs attached to them, so for this chord it would be arc AB, and then for this chord it would be arc CD, those measures would have to be equal. On the flip side, since we're allowed to read that sentence backwards, if we were to see that the arcs had the same measure, so maybe there's congruent marks or maybe these are both 60 degrees, then we would be able to conclude that these segments attached to them are congruent as well. For biconditional number 2, a radius is going to be perpendicular. We used that word in the last lesson, that upside down T, that means that it forms a right angle. So a radius is perpendicular to a chord of a circle if and only if it bisects the chord. That bisect word is back from first semester. When something's bisected, it's divided exactly in half. So we'll know that a radius, or in this case, it's actually two radii drawn in together, so a whole diameter, is perpendicular to a chord if and only if, when we look at the chord, it's divided exactly in half. So those two segments, segment AB and segment CB, have to be congruent. If we were to read that biconditional backwards, then we would start with these congruent marks. So we would see a chord that's divided up into two equal parts, and then we would be able to add this right angle onto the picture as a result. So if we see the right angle, we can put the congruent marks on the diagram, and if we see the congruent marks, we can add the right angle to the diagram. For biconditional number 3, chords are going to be congruent if and only if they are equidistant, or the same distance from the center of the circle. So when we see this little perpendicular segment connected to the center, marked with a congruent symbol that matches this little perpendicular segment connected to the center of the circle, that tells us that our chords, AB and CD, are going to be exactly the same size. So we're able to make the conclusion that AB is congruent to CD. Again, if we read that one backwards, it's also true. So if we saw that these chords were the same size, then these little perpendicular segments from the center would be able to have congruent marks added onto them. All right, those are our 3 biconditional statements that are true when we're dealing with chords. So now we're going to jump into the examples and see how they will help us to solve problems. Looking at question number 1, we have information about 2 chords. If we were to make an educated guess, we would probably guess that x is equal to 12 just because 12 is the only segment in the picture, but we need some justification. We need reasons for why. So I'm thinking that we're probably going to use biconditional number 1 up there, where if we can show that this arc matches this arc, then it forces those chords to be congruent as well. Thinking back to our previous standard, if this is the only arc that's missing in the circle, we can do some subtraction from 360. So if I subtract 220 and I subtract 70, sure enough, I end up with 70 degrees as the measure of that third arc. And so now I see that I've got 2 arcs that are congruent, which then forces these 2 chords attached to the arcs to also be congruent, giving me the evidence that I need to say that x is equal to 12 centimeters. Looking at example B, it looks a little bit more complicated. We've got a segment, a chord that's equal to 10 centimeters. We have a different chord that's equal to 11 centimeters, and then we're being asked to find the measure of a third chord. I can tell the arcs attached to each of these original chords. There's a little overlapping piece there, so we need to be a little bit careful. The arc attached to IJ would be 55 plus 25, which is 80 degrees. And then the chord, maybe a different color would be helpful. The arc attached to chord HA would be 25 plus 60, which is 85 degrees. So what I need to figure out is what this arc measure is equal to. Hopefully it matches one of these 2, so I'll be able to steal one of those 2 segment lengths. Now be careful when you're solving for this arc that you don't double count. So we don't want to use the 80 and the 85 that we just marked out. We want to use all of the individual arcs around that circle as we're subtracting from 360. So 140 and 55 and 25 and 60 would represent all of those non-overlapping arcs that the circle is formed by. Subtracting all of those is going to leave us with 80 degrees for the arc between A and K. That matches the arc between I and J. So that means that this IJ chord, kind of highlight that in a different color, is going to be congruent to this AK chord. IJ was equal to 10, so that now gives me my measurement for AK, also equal to 10. So both of those are examples of biconditional statement number 1 up above. Moving to letter C, I'm seeing something a little bit different. I've got segments connected to the center, but they're not full radii. They do have right angles, and they're marked as congruent. So this little setup is showing me that these 2 chords are both the same distance from the center of the circle. If they're the same distance from the center of the circle, then they're equal. That's biconditional number 3 up above, right here. If they're the same distance from the center, then they're equal. However, I only see this little piece of the chord labeled as 3.5. So I'm going to actually need to use biconditional number 1, or not number 1, excuse me, biconditional number 2 to help me out as well. Except in order to use that, I have to actually extend this out a little bit farther so that I can see it as a radius. So now what we have is a radius that's perpendicular to a chord, which means that this chord is bisected. That 3.5 centimeters is going to match this other side. So together, the whole chord is going to be 7 centimeters, and that whole chord is what we're looking for when we're looking for x. Again, they're congruent because they're equal distances from the center. These pieces are congruent because that segment from the center makes a right angle and is perpendicular to the chord. So combining those second and third biconditionals together, we can land on x being equal to 7 centimeters. All right, go ahead and flip to the examples on the back side of the page and we'll meet you back here to finish them out. All right, as we continue our work here, we have a segment that is passing through the center of the circle, making a right angle with this chord. Now this segment could be extended down to be a radius, and so what we have here again is biconditional statement number 2, where a segment through the middle of the circle is perpendicular to a chord. That means that that 24 centimeters is going to get split in half, 12 centimeters on the left and 12 centimeters on the right. My actual goal for this problem is to figure out what segment AC is equal to. AC, if I draw it in, is a radius of the circle. I don't see any other radii of the circle completely labeled. So I think that right angle, as well as being able to split that 24, is going to help me to solve for AC using my Pythagorean theorem. AC would be the hypotenuse across from the right angle, so that would be the c-squared part of the formula, and then 5 and 12 are the other two sides of that right triangle. X squared will be 25 plus 144, which simplifies to be 169. And then that's a perfect square that gives me an answer of 13. Technically a positive or negative 13 because we're square rooting, but because it needs to represent a segment, only the positive answer will make sense. All right, on to example B here. Again, we have a segment coming from the center of the circle that is perpendicular to a chord. If that were extended out as a full radius, then we would see a radius perpendicular to a chord, which means this chord is bisected. None of that really seems super helpful, though, in terms of finding the x. There's not another chord somewhere else that would be congruent to it, so there must be a way to use this 6 centimeters to help us out. That would be a radius. So I'm thinking if I rotate that through and I make another triangle, kind of like we did on the previous problem, that radius would match this radius, so I would be able to label this as 6 centimeters. And then I would be able to find this side of the triangle, which then will help me track down my x. I'm not going to use x as my variable, though, because I don't want to get confused and think I'm done with the problem before I actually am. Thinking about Pythagorean theorem, since I don't have any other angles other than the 90, the 6 would be the c squared, and then the 3 would be either the a or the b. So I'm just going to leave b as my variable right now. That would be this little segment here. 36 is equal to 9 plus b squared. We're going to subtract 9, get 27. And then this is a little bit trickier than the last time I used Pythagorean theorem because 27 is not a perfect square. So if I take a quick check at my instructions, it does say that the goal is to give exact answers. So this is where factor trees, factor tables, perfect squares would be needed. If you try to square root 27, it gives you a decimal, which is why we're going to go through that more complicated process. If you're a factor table person, 1 and 27 don't have any perfect square factors. 2 doesn't work, but 3 and 9 would be the set of factors that would work. If you're a factor tree person, maybe you split it up to be 3 times 9 and then 3 times 3. So you've got a set of matching 3s and a leftover 3. Or if you're a perfect square person, you could rewrite 27 as 9 times 3. In all of these cases, when you square root 9 or find that set of 3s, that means there's going to be a 3 outside the root, and then the leftover number in all cases is also a 3. So b is equal to 3. Now when we look at b, there's actually 2 of those end to end that form that whole entire segment marked with the x. So if I take 2 of those, it's going to require me to double that answer, and x is going to turn out to be then 6 root 3 centimeters. All right, we have 2 examples left here, and both of these, our goal is to solve for x. So taking a look at letter C, I'm noticing again that I have a segment coming from the center of a circle making a right angle. So that tells me that these two little portions of that chord are going to be congruent. I also can see that I've got a 12 marked as the radius, and another 12 would be up here then, because that's a second radius, which does mean that these two little triangles are congruent. This would be a right angle, and then we've got hypotenuse leg theorem happening there. Now, the reason why that's helpful is because I don't have enough information for Pythagorean theorem, but I do know this arc out here. So from our standard 17 work, if that arc is 60, a central angle would be 60 as well. But in addition to that, we've got two congruent triangles. So I'm able to take that 60 and actually split it half and half to give me two little 30-degree angles. That means that I'm dealing with a little 30, 60, 90 situation. If 12 is across from the 90 degree, that's going to be 2 times the shortest leg. So if we divide that by 2, that shortest leg across from 30 will be 6, which means this shortest leg across from 30 is 6. Combining those two 6's together is going to give me a 12 for the value of x. All right, one final example with these chord biconditionals. We've got a chord that's 120. We've got a radius that's 8, and we're looking for an arc that's 120. Sorry about that. A radius that's 8, and then we're looking for this chord. I think I'm going to draw in a second radius, which would also be 8 centimeters. This 120-degree angle would match this angle here at the center, because central angles and arcs have similar measures. And I think I'm just going to recreate the same type of deal that we had before. If we were to drop down through the center a perpendicular, that would split that 120-degree angle in half. It would give me 60 and 60. Sorry, that's kind of small. And so then I would have the same kind of situation where the hypotenuse is equal to 8, which means that my shortest leg, which would be here, would be 4. And then the longer leg would be 4 root 3 in both of these little back-to-back 30, 60, 90 triangles. So my full length for x all the way along that chord would put those two 4 root 3's together, and we would end up with 8 root 3 centimeters as the value of x. All right, that's all there is for chords today and the 3 biconditionals related to them. We will see you back in class. Thanks for watching.